Hello viewers, welcome to video number 100 of the channel MALACHEMPHILIC, and video number 100 is the 41 episode of Chemical Thermodynamics, and the topic is number 1, entropy change in mixing of ideal gases, number 2, entropy change in reversible phase transition. Okay, so let's start. So our first topic is entropy change in mixing of ideal gases, right? Now just to consider, this is a chamber. It is separated by this partition. Here you have gas 1, ideal gas. Here it is gas 2. And if you remove this partition, gases will mix up. So before mixing, the volume of gas 1 is V1. Volume of gas 2 is V2. Number of moles of gas 1 N1. Number of moles of gas 2 N2. Pressure of both the gas, that is gas 1 and gas 2 before mixing, and after mixing also same. That means pressure is constant. Similar way, temperature also, gas 1 and gas 2 also same. After mixing, that mixture temperature also same. That is temperature also constant, right? Now if you remove this partition, the gases will mix up, right? Now we know that common equation for the entropy change that already we have derived for the ideal gas, that is delta S is equal to NCV ln T2 by T1 plus NR ln V2 by V1. This equation already I have derived. Now first I will apply this equation for gas 1. Okay, gas 1, so delta S1, that will be is equal to, if I apply this equation, temperature is constant, so this part will get cancelled. So what it will be, N1 number of moles R ln V2 here means V final volume divided by initial volume. Okay, for gas 1, initial volume is V1 and final volume, that will be entire space, that means V1 plus V2. So what I can write now, delta S1, that will be is equal to N1 R ln V final is V1 plus V2. V initial means V1. Okay, right. Now we know that for ideal gas, what we know? PV is equal to nRT. Now we will apply this for this gas 1. Okay, then what it will be? PV is equal to nRT. For gas 1, initial state, pressure is constant P, volume is V1, number of moles N1, R, T. This is for the initial. Okay, and in the final state what we can write? Pressure is same, as I told you, after mixing also you are considering pressure same. Volume is V1 plus V2. Number of moles is N. N means N1 plus N2. Total number of moles. N is equal to N1 plus N2. After mixing, it will be total number of moles. That is moles of gas 1 and number of moles of gas 2. Right. So from here, what I can write? So from here I can write V1 is equal to N1 RT by P. And from here I can write V1 plus V2 is equal to nRT by P. Okay. Now this V1 and this V1 plus V2, I'll put it in this equation. So what it will be? Our equation is delta S1 is equal to N1 R ln V1 plus V2 divided by V1, right? So I have to put V1 plus V2 is equal to nRT by P. So N1 R ln, this one is, as just now we have derived, nRT by P, and V1 will be N1 RT by P. So it is nRT by P divided by N1 RT by P. So delta S1, that will be is equal to N1 R ln, what it is, nRT by P into P divided by N1 RT. See, PP cancel, RT cancel. So what is left over? Delta S1 is equal to N1 R ln N by N1. And this one I can write it as minus N1 R ln N1 by N. This is log. Ln means log base E. So if I write N1 by N, so it will be minus. In the similar way, I can write delta S2, that is entropy change of the gas 2 due to mixing, that will be is equal to minus N2 R ln N2 by N. Now, then what is the total entropy change during mixing or entropy of mixing? That will be delta S1. Here I'll write S2. I have taken the Roman 2. Okay. Plus delta S2, that will be is equal to minus N1 R ln N1 by N minus N2 R ln N2 by N. Okay. Now, so delta S mixing, I can write it as, if I take minus common, then N1 R ln N1 by N, that is number of moles of the component divided by total number of moles, that is the mole fraction of gas 1, plus N2 R ln, similar way it is mole fraction of gas 2, right? Little more I'll modify this equation. I'll divide and multiply by total number of moles, that is N. Then what it will be? Delta S mixing, that will be is equal to minus, here N1 divided by N, total number of moles, R ln X1 plus N2 divided by N, R ln X2, okay, into N. Divide and multiply it. Okay. So this one is equal to minus N, and this R also, if I take outside common, N1 by N is X1, X1 ln X1 plus, this is X2, X2 ln X2. This is the equation. That is for delta S mixing. So, during the mixing of ideal gases, the entropy change is this one. So here negative sign is there. Does it mean that entropy change is negative or entropy decreases during mixing of ideal gases? No. Because look at here, ln x1. x1 is the mole fraction. Mole fraction is less than 1. ln less than 1, point something, that means negative. Okay. So mole fraction is 0.2, 0.4, whatever it is. That means ln of point that one, that will be negative. So negative will be positive. So entropy of mixing, that means entropy change during mixing of ideal gases is positive, or entropy increases during mixing of ideal gases. Now our second topic is entropy change in reversible phase transition. Phase transition means transformation of the physical state. Say for example, solid to liquid. This is your fusion. Okay, and all of you know that solid to liquid means fusion or melting. The melting start at a particular temperature. Say for water it is ice and water system, that is 0 degree centigrade, and the temperature remains constant till all the solids converted to liquid. Okay, similar way vaporization, liquid and vapor. Okay, this is vaporization or boiling. Okay, so vaporization, or here it is boiling, it starts at a constant temperature and temperature remains constant. Of course pressure should be constant, atmospheric pressure. Under constant atmospheric pressure, all the liquids converted to vapor at a particular temperature. Though you are supplying heat, temperature will not change. Temperature remains constant till all the liquid converted to vapor. Why temperature remains constant? You are supplying heat. Say for solid. Solid molecules are close to each other. So intermolecular forces of attractions are more. Right? So the heat supplied is utilized to break those intermolecular forces. Therefore, temperature is not increasing. Similarly for liquid and vapor. Liquid also molecules are comparatively closer than vapors. Molecules are far away. Practically no intermolecular forces of attraction. So to break that intermolecular forces of attraction in liquids, that supplied heat is utilized. So temperature is not increased. That's why this heat absorbed during this melting or during this vaporization or heat release during freezing, during condensation, these are known as latent heat. Latent heat of fusion, latent heat of vaporization, like that. Okay. And see, at melting point or during fusion, at melting point, these solid and liquid phases are in equilibrium. Similarly, during boiling, liquid and vapor phases are in equilibrium. So equilibrium is maintained. So it is a reversible process. So entropy change, say during fusion, that will be is equal to Q reversible. Q reversible means that heat absorbed at constant pressure reversibly divided by temperature of fusion. That means it is the melting point. And from first law we know that heat absorbed at constant pressure goes to increase the enthalpy. So that is equal to enthalpy change, or it is known as, here it is enthalpy of fusion divided by this melting point. Okay, and remember this enthalpy of fusion, this is for 1 mole. So therefore entropy of fusion is for 1 mole. Okay, so this is delta S fusion for 1 mole. That is equal to delta H fusion. This is also 1 mole, already I have written, divided by melting point. So from here we can write delta S fusion into this melting point is equal to delta H fusion. Similar way, delta S vaporization, that will be is equal to delta H or enthalpy of vaporization divided by this is boiling point. This is also for 1 mole. So entropy of vaporization for 1 mole is equal to enthalpy, molar enthalpy of vaporization divided by boiling point. Similarly, reverse one, if you consider freezing, energy will be released. Okay. In that case, energy will be released during freezing or during condensation, that is vapor to liquid. Energy will be released. Okay. Now, in this case, during fusion, during vaporization, heat is absorbed. Okay. So, therefore, this Q reversible is positive. So, entropy change or entropy of fusion, entropy of vaporization is positive. During these processes, entropy increases. But the reverse process, that is liquid to solid, freezing, vapor to liquid, that is condensation, heat is released. So, heat is released means Q reversible is negative. So, it is minus delta H freezing, okay, enthalpy of freezing. So, as it is minus, this entropy change is negative. That means entropy decreases during freezing or condensation, increases during fusion or vaporization. So, this is all about the entropy change in reversible phase transition, which is the change of physical state, and it is reversible because at that particular temperature, melting point or boiling point, two phases are in equilibrium. Hope you have understood. Thank you.